Welcome to the deep dive. So today we're going to get into a really specific but critical problem in a lot of big infrastructure projects. We're talking about the physical distance requirement for GPS signals. For anything that needs precise timing or navigation, you've always had to keep your gear practically on top of the antenna.
That's the core of it, exactly. You're running a universal time receiver, maybe some mission-critical nav gear, and that signal is usually on a coaxial cable, right? Which means you're stuck within, say, 100 feet of the antenna.
100 feet. And that sounds like a lot, but if you're talking about a huge naval vessel
Or a military bunker, deep underground that needs a clear view of the sky, that 100-foot rule becomes a huge liability. It forces some really awkward, sometimes very vulnerable placements.
And that's exactly what we're going to dig into today, this technical solution that just shatters that limitation. We're talking about GPS over fiber systems. Specifically, we'll be looking at the architecture of something like the Thor Broadcast F-1GPS-TXRX. Okay, so let's unpack the mechanism first. You're taking the signal from a standard copper coax cable
Right at the antenna.
and converting it immediately to fiber optic. What does that actually buy you in real-world terms?
It buys you freedom. Geographical freedom. That 100-foot constraint, it completely vanishes.
Vanishes.
Gone. It's replaced by the ability to link your antenna and your gear over 20 kilometers away.
20 kilometers. That's over 12 miles?
Over 12 miles, yeah. This allows for massive, geographically spread out synchronization that was just, impossible before.
Okay, but my first thought when you add that kind of distance is, what about the signal integrity? Are you compromising the quality for all that length?
That's the beautiful part of the engineering. Fiber actually, and this is kind of counterintuitive, it dramatically increases the signal integrity.
How so?
Well, for one, it supports all the international GPS frequencies. We're talking L1, L2, all the critical bands. So you get a solid lock anywhere. And second, because the signal is now light, not electricity.
It's immune to interference.
Exactly. Completely immune. Think about a noisy broadcast tower or a factory floor. Coax picks up all that stray RF noise. Fiber doesn't.
That's a huge plus. But let's talk about protection. You mount an antenna way up high. It's basically a lightning rod.
It is. It's a critical single point of failure. And this is one of the biggest, maybe the biggest benefit of this fiber architecture. You get total electrical isolation.
You're physically decoupling the antenna from your expensive equipment.
Precisely. A lightning strike hits that antenna. That massive surge just stops. It cannot travel down the glass fiber to fry your, multi-thousand-dollar timing board.
And I've got to imagine there's a security angle here too, especially for military sites or R&D facilities that are piping really sensitive time data around.
A huge one. Fiber is notoriously difficult to tap without being detected. Much, much harder than putting a tap on a copper coax line.
So it's inherently more secure.
It is, and these systems often build on that. They include a physical security break feature, which gives you an alert if the link has been compromised. A tamper-proof connection.
So the ideal environments are these extreme ones: broadcasting towers, cell sites, military installations.
Large ships, absolutely.
What really stands out to me, though, is the flexibility, the idea that you can support a high level of optical and RF splitting.
Yes. And if you connect that to the bigger picture, that splitting capability is just transformative for how you design your infrastructure. It means you can have one single, perfectly placed antenna system, and that one GPS signal can be split and run to dozens, maybe hundreds of individual timing boards all over a campus.
So every single component gets the timing it needs from one source.
Spread out over a massive area. And we should just briefly mention, these systems are built for those harsh environments we talked about.
Right, they're not delicate.
Not at all. Yeah. We're talking an operating temperature range from -25 all the way up to +70 degrees Celsius. They are true industrial-grade deployments.
So to kind of sum this all up for you listening, what this shift really means is that you can finally put your critical timing and navigation gear where it's safest, where it's most accessible. It's totally independent of where the antenna has to be, and you're actually increasing your security and signal quality at the same time.
Which leaves us with a final question, a thought for you to really mull over. If you can now deliver absolute time and position data securely, reliably, with no interference across 20 kilometers, what new possibilities does that open up for things like infrastructure, for R&D facilities that up until now have had to compromise because they were stuck with localized, vulnerable, copper-based systems?